So far, our techniques of differentiation and finding derivatives have worked really effectively for finding functions that can be written explicitly in terms of another variable, meaning things that we can say f of x equals things like the square root of x squared plus 1. Or if we were to use a variable, we could say y equals x squared plus 1. Or we can do things with sines and cosines as well. You know, cosine of x times e to the x. Things like this we've been able to deal with reasonably well. What our techniques so far wouldn't be able to do would be something that's not what we typically think of as a function. So if we look at the equation of the circle, x squared plus y squared equals 9. So here I have the graph of that circle. I have a point labeled. What I would like to eventually do in this problem is find the equation of the tangent line to that circle at that point using some of the techniques that we've learned already, modified a little bit. And this technique that we're going to use is called implicit differentiation. And the reason we call it that is because this is an implicitly defined function. It's not an explicit function in the way that those first few functions we looked at were. This is what we'd call implicit. So the method that I'm going to use to find this derivative is I'm going to replace this y with f of x. And I'm just using this for a placeholder and to remind myself sort of what is happening here. In some ways, this is not technically correct, but it is almost a mnemonic device for helping me get through this derivative. So what I'm going to do is I'm going to write this as x squared plus f of x quantity squared. From here, I want to take the derivative of both sides with respect to x. So if I take d dx of both sides of this equation, well, okay, so we'll get the derivative with respect to x of both sides here. And I'll split this up on the left-hand side here. And as we take the derivative here, the derivative with respect to x of x squared is just 2x. And I'll skip over the derivative with respect to x on the right of that constant is just 0. Now, the interesting bit is this part with that I replaced, this d dx of f of x quantity squared. So here, to take this derivative, I have a function squared. So the way I want to think about that is using the chain rule in the way that we have before. So in the middle bit here, I'm going to have 2. So I bring down that 2, subtract 1 from the exponent, leave the inside alone, this f of x, and then you take the derivative of the inside. Now, I don't necessarily know what that derivative is, but I can still denote it with f prime of x. Okay. Now, once I've taken this derivative, I want to solve for f prime of x. So I want to get everything else over on the other side of the equation and go from there. So first thing I would do is I would subtract this 2x over to the other side. So I get negative 2x. And now I've got 2 times f of x times f prime of x. This is the thing I care about, times something. So what I can do is divide by the 2 f of x here, and I get f prime of x equals negative 2x over 2 f of x. And once I've done this, I want to replace the f of x with y again. And in particular, also, anytime I have a f prime of x, I'm going to replace it with a y prime. So the derivative with respect to y, this y prime that we've sort of done before, will be negative 2x over 2y, which I can simplify as negative x over y. And here is my formula for the derivative with respect to y that we've been using before. It's just got an x and a y in its solution. So let's find the tangent line, the equation of the tangent line. The point is 3 times the square root of 2 over 2. 3 times the square root of 2 over 2. That is that point on the circle that I have there. So to find that derivative, we would plug that in, those x and y in. So we'd have negative 3 square root of 2 over 2 divided by that same thing. And so we'd get that the slope of that tangent line is negative 1. So we go ahead and type that, or plug that into our formula for the line through that point with the slope that we care about or have found. And so we do our normal tangent line thing and we get this. And let's go ahead and look at the graph and see what we can see and see if this is a reasonable answer. And we plug it in and we see that this looks good for our tangent line here. And a couple of other features I want to point out about this based on what we've just found. So this derivative is negative x over y. So notice that when y would equal 0, we would have an undefined slope. So that would be a vertical tangent line. And if the numerator is 0 and the denominator isn't, we'd have a horizontal tangent line. So let's look at where that's happening in our graph here. So a vertical tangent line would be at 3, 0. And you can imagine the tangent at that point on the circle, that would indeed be a vertical line at when the y value is 0. And the same thing on the other side at negative 3, 0, you would have this vertical tangent line. And when x equals 0, that's where you're at the top and bottom of this circle. And that would be where you would have a horizontal tangent line. So the derivative that we found matches what we would expect to have happen by what we know about tangents on this circle. Now, for another example of an implicitly defined function, let's look at x squared plus 2xy minus y squared plus x equals 2. This is an example of what we call it a hyperbola. And again, it's not a function. It fails the vertical line test here. But let's go ahead and try to find the slope of the tangent at this point 1, 0 on our hyperbola. We have this function and we are trying to find the slope of the tangent line, or the equation of the tangent line at 1, 0. All right, so again, I'm going to start by replacing y equals f of x, and then eventually y prime will equal f prime of x. So I'm going to go through and make those changes. So x squared plus 2x times f of x minus f of x quantity squared plus x equals 2. Now we're going to take the derivative of both sides of the equation. So we have d dx of x squared plus 2 d dx of 2x f of x minus d dx of f of x quantity squared plus d dx of x equals the derivative with respect to x of 2. So some of these are straightforward things we've done before. Derivative of x squared is just 2x. The derivative of x is just 1. And on the right-hand side, we get 0. So the ones that we have to think about are the ones that have the f of x in them. And so this first one, we've got a product rule happening because we have 2x times f of x. So we can think of that 2x as a function times this f of x. So if we leave the first alone and take the derivative of the second, we get 2x times f prime of x. And then we'll add what we get when we take the derivative of 2x, which would be 2, and leave f of x alone. And then on the second bit, we've already done one like this with f of x squared, so we bring that 2 down times f of x, and then we take the derivative of the inside, and we get f prime of x. And we get this equation equals 0. And again, we want to solve for f prime of x. So I want to get the f prime stuff together on one side. So that means I'm going to start by subtracting the terms that don't have an f prime. So we will get 2x f prime of x minus 2 f of x f prime of x equals, and so we subtract over the minus 2x, the minus 1, and minus 2 f of x. So that was subtracting the terms highlighted in blue over to the other side. Now, on the left here, both of these have an f prime of x, so we can factor that out. And we will have 2x minus 2f of x, quantity times f prime of x. And so to finish solving for f prime of x, we just need to divide by that sort of coefficient out front there, that 2x minus 2f of x there. So when we do that, we get 2x minus 2f of x. And then to finish, we would go ahead and replace the f's with y's again. So we'd have y prime is equal to negative 2x minus 1 minus 2y over 2x minus 2y. Now, we wanted to know the value at 1, 0. So we are plugging in both values here. So before we've been able to get away with just plugging in x. Here we need to plug in the x and the y. So at 1, 0, we have y prime is equal to negative 2 times 1 minus 2 times 0 over 2 times 1 minus 2 times 0. And as we simplify there, we'll get negative 3 in the numerator and we'll get 2 in the denominator. So we get negative 3 halves. So our slope of our tangent line is going to be y minus 0 equals negative 3 halves times x minus 1. Let's go ahead and check the graph. And we go ahead and graph that, and it does indeed look the way we expect a tangent line to look there.